So in the Indian code, a modified version of this, which uses 4 curves, has been adopted. And this particular adoption is similar to what is done in the British code. And it is based on an approach named Robertson approach. Now it's okay if we don't remember this name, but what's important is we know why we have 4 curves, and today we are going to learn to use these curves so that we can design the columns that we are going to actually use. Now, just before we actually get into design, there's one more concept that I want to cover, and after that we can get to designing columns.
I have a question from the previous lecture.
Yeah.
Can you explain how to? You spoke about normalizing the curve, and I didn't understand that. Yeah, this one thing.
So when we normalize the curve, what we are doing is we are just minimizing the number of variables in a particular curve. For example, in the curve you see here, there's FCR, there's lambda. So we want everything in terms of only, say, one of those. So what we do is we normalize it, meaning that we divide the y-axis by fy and we divide the x-axis by lambda p. So fy upon fy is 1. So this curve, which was this axis, which was initially FCR, is now FCR upon Fy. That is what we see here. And here we divide the x-axis by lambda p. So this, which was lambda p previously, now it's 1. And this axis, which was lambda, is now lambda upon lambda p. And last time we derived as to how lambda upon lambda p is equal to square root of Fy upon FCR. So now you see in this entire curve, there's only one variable, that is FCR. Fy is something that we already know. So the only variable is FCR. So it is just a process of minimizing the variables in a curve. And that is how these curves are ultimately represented. Okay.
All right, thank you.
Yeah.
So it's not perfectly accurate, but just experimentally accurate, right?
What?
It's not theoretically accurate, it's just experimentally accurate, right?
It is a collusion of theory and practice as well. It takes into consideration, it is based on the theory that Euler gave, and it considers all the practical aspects.
So it's a mixture of like the theory, what the math should do, and what the material actually does in real life.
Yes. Instead of the material, saying the material instead of the member, what the member does. Okay. So I believe you must have heard of this term called effective length. We've said that the strength of a compression member is a function of its length, or rather being more specific, it is a function of its effective length. So we're going to learn what effective length is and how actually does it affect the strength of a compression member. Now, first, let us look at the formal definition, and then we bring it down to basics, and then try to understand it. So, effective length of a compression member or effective length of a column in a given plane, in a given plane, because there are two principal axes, and the bending can occur either of about either axis. Therefore, we always define effective length in terms of the plane in which it bends. So effective length of a column in a given plane is defined as the distance between points of inflection in the buccal configuration of the column in that plane. Now, this might sound very difficult, but actually it's very easy. So, just imagine a pin-ended column. Just look at, the diagram A here. Now, this is a pin-ended column, meaning that both the ends are simply supported. When we apply axial compression, at some point of time, this is going to buckle. And the buckle shape is going to be more or less what you see as a dashed line. Now, in this buckle shape, we observe that there is no moment here and there is no moment here. And the points along the length of the member where the moment is 0 is called as a point of inflection. So what this says is you just measure the distance between points of inflection when the column buckles. So imagine this is a pin supported column, you apply load here, the column buckles. Now just measure the distance between points of inflection or points that have 0 moment. Now since it is simple support, obviously the moment at the support itself is going to be 0. So in this case, the effective length is equal to the unsupported length. So here, the term K, which is called as effective length ratio, it is the ratio of the unsupported length to the effective length, is 1 in this case. Now let us take another example wherein both the ends are fixed. Now in this case, the buckle, if you apply axial load here, this is going to resist, this support is going to resist rotation here. And therefore you see the buckle configuration is something like this. And we'll expect, okay, I'll let me take a step back and make it, simpler. So just imagine that this is a simply supported beam. So if we have, so let us say it is subject to uniformly distributed load. Now, if we look at the deflected shape, it will look something like this. This is our deflected shape. The moment here is 0, moment here is 0. Now, if I draw the bending moment diagram, it is also going to look something like this. The moment here is WL squared by 8. Moment here is 0. Moment here is 0. So this is the length that we are looking at. The length between points of inflection or points of zero moment. Now let us say I convert these supports into fixed supports. Now if I apply UDL here, the deflected shape is going to be something like this. This is our original shape. The deflected shape is going to be something like this. So it is initially going to resist it, and then again something like this. So here, if I look at the bending moment diagram, it is going to be something like this. Okay, so up to this point, there's a hogging moment, then there's sagging moment, and there's hogging moment. So for such a support, this is our effective length, the length between points of inflection. So as we change the support conditions, the points of inflection shift their position. For example, when we have a simple support, the points of inflection are at the support themselves. But when we have a fixed support, the point of inflection move inwards. If there's a third condition, say where one of the supports is pinned and the other support is fixed. In this case, the deflected shape would look something like this. So here there will be no resistance to deflection, rotation, and then here something like this. So if I look at the bending moment diagram, the bending moment diagram would be something like this. So then we are looking at the distance between these 2 points. So the distance between, now just apply this to columns. So a column is nothing but this is a vertical member, then there's some form of support. Then you're going to apply an axial load here, but ultimately it is going to bend like this. It is going to buckle like this. So if it's a simple support, it is going to buckle like this. If it's a fixed support, then it will buckle like this. So I just draw it here so that this clarity. It will buckle like this. Then if one of the supports is pinned and the other support is fixed, then it will buckle like this. So there will be some resistance for rotation here, but here there will be no resistance of rotation. In this case, it will be the distance between these 2 points. In this case, it will be the distance between these 2 points. So this is nothing but effective length. So when we have pinned supports, the effective length factor K is equal to 1. When we have fixed supports, the effective length factor K is equal to 0.5. When we have one end that is fixed and another end that is pinned, the effective length ratio or the effective length factor is equal to 0.7. Now, You've learned this before, right? This is not the first time that you're learning this.
Yeah, we did it. We did this last year.
Okay. So this is what what effective length means. Now, what do these numbers stand for? Say 0.5, 0.7, 1. What do these numbers mean? Now, perhaps this might be something that you learn for the first time. So let us say that we have a pin-ended column. For this a pin-ended column that has an unsupported length of L. For this pin-ended column, our K value is 1. Now, let us say another column that is fixed-ended. It also has an unsupported length of L. For this column, K is equal to 0.5. Okay. Now let us see what impact does this K is equal to 1 and K is equal to 0.5 have on the load carrying capacity of the column. So from Euler's formula, we know that PCR, or the critical buckling load, is equal to pi square E upon KL upon R. Okay, just a moment. I should have written stress here. So the critical stress FCR is equal to pi square E upon KL upon R square. Now here K is equal to 1. Therefore, for the first case, this is equal to pi square E upon L by R square, because K is equal to 1. Now for the second case, let us say this is our first case, this is our second case. For the second case, FCR is equal to pi square E upon KL. So K is 0.5. So I can write it as 1 by 2 square. And I just separate this L upon R square. So this turns out to be 1 by 2 square is 1 upon 4. 2 comes to the numerator. This is equal to 4 into pi square E upon L upon R square. So this is equal to 4 times of the capacity that we get using pin supports. So just by changing our supports from pin to fixed without changing anything else, without changing the length, the material, the cross section, our load carrying capacity is 4 times that of a pin-ended column. So that is how much the support conditions can impact the load carrying capacity or the strength of compression members. And that is why it is extremely important that we understand the effect of end restraints on the strength of compression members. Another way of understanding the 0.5. So what does this 0.5 mean? So if I have a pin-ended column, that has an unsupported length of 0.5 L, this column and this column would have the same strength. Do you understand? Okay, I'll just repeat this. So when we say that K is equal to 0.5 for a fixed ended column, what it means is that the strength of a fixed ended column of length L is equal to the strength of a pin ended column of length 0.5 L. Do you understand this?
Yeah. Yes.
Simple, right? Similarly, if you're talking about a column that whose one end is pinned, so for a column that has one end as fixed, another end as pinned, and has a length of L, the buckling strength of this column is equal to the buckling strength of a pin-ended column that has a length of 0.7 L.
I think we had a similar concept last semester as to this on the end conditions and how it affects the vertical numbers in compression.
Perfect, then it might be easier for you to understand this.
The concept is similar, that why it's getting the length is, we had it was a matter of length. There was a factor you added the length to get the length the load is acting upon, rather than just the actual length of the column. Because when both ends are fixed, it only acts on half the length of the column, right? The load. Or the deflection isn't half the column, rather. Something similar concept. There's an effective length and an actual length.
Mm-hmm.
So this is similar, but I think the numbers are very different. There was a repro involved last time somewhere.
Mm-hmm.
This is just more simpler because it's like a scaling like 0.5, 0.71. Simpler that way.
Okay. Okay. So is there any question here? Okay, so we just looked at two ways of understanding what effective length factor K is. One is that it is the distance between one, that it is the ratio of effective length to the unsupported length, and effective length is nothing but the distance between points of inflection in the buckled configuration of the column. And second is in terms of relative strengths of columns with different end restraints and their lengths. So this is the second concept that we looked at. This is the second way of understanding what K means. Okay. So what we looked at are called as the ideal boundary conditions. So a perfect pin or a perfectly fixed support. These are idealized boundary conditions. Okay, I could have used this formula as well. Anyway, I think the concept still remains the same. So all this is valid for what are called as idealized boundary conditions. But in actual practice, what happens is we cannot achieve these perfect conditions. We cannot achieve a perfectly fixed support, or we cannot achieve a perfectly pinned support. There's always some rigidity, or there's always some flexibility in the support, as a result of which it can never be a perfect pin, or it can never be a perfectly fixed support. Therefore, what the code does is, and again, this is again, this is again something wherein we are trying to, fuse theory and practice. Because if we go on with, say, assuming that both our supports are fixed, assume the value of k to be 0.5, we might get a strength that the column might not actually be able to achieve. So again, we might deviate from the experimental results and we say that this theory is not good. And therefore, again, the code sort of takes a judgment, considering that we cannot achieve a perfectly fixed support or a perfectly pinned support in practice. Therefore, based on these values, based on the theoretical values that that we get from this concept, the code gives its own set of values from these values. For example, if both the supports are fixed, theoretically the value is 0.5, but the code says that the value that should be used is 0.65. If one support is pinned, other support is fixed, instead of 0.7, take the value to be 0.8. Now, in case of a perfectly pinned column, in case of a pin support, it doesn't really matter, because that is a basis for defining the values of k. Therefore, the code keeps the value as 1. And the other support conditions, we're not going to get into those as of now. We are going to deal with only simple conditions, like both supports pinned, one support pinned, one support fixed, and both the support fixed. As simple as that. And so we can say that a particular support is perfectly rigid. Now, a few examples of a perfectly rigid support are when a column is anchored securely in a footing in such a way that there's no scope for rotation. That support can be called as a perfectly fixed support. But over the height of the structure, when a column is connected to a column, maybe we don't have a perfectly fixed support. Therefore, we have a partial support. And in that case, we use the values that are given by code. Now, so by now, one thing is clear that smaller the value of k, lesser is the susceptibility of the column to buckle, and greater is the load carrying capacity of the column. Just as we looked at the load carrying capacity of a fixed column, comparing it with the load carrying capacity of a pin column, we saw that the load carrying capacity of a fixed column is 4 times that of a pin column. So smaller the value of k, lesser is the susceptibility to buckling, and greater is the load carrying capacity of that particular column. Now, perhaps you could answer this question. Now, when we adjust these theoretical values so that they can be practically used, why is it that we increase these values? Why say the code does not reduce this value of 0.5 to 0.4? And why does it increase the value of every time?
Because you have to
Because not all. Go on first, sorry.
No. I was saying that we have to underestimate the capacity.
Exactly. See, we know that it is inversely proportional to the effective length. So if you sort of change the value from 0.5 to 0.4, it is going to increase your strength. That is not really the direction in which we are moving. We are trying to underestimate the capacity. We are trying to come up at a safe number of the capacity. And we can do so by increasing the value of k, because strength is inversely proportional to KL. Therefore, increase the value of KL to sort of get a reduced value of strength.
And
Is
then
that clear?
lastly, why? So in the lastly, can I make a guess as to why it stays the same instead of increasing?
In which one?
The last three, the three towards the right, can I make a guess as to why it stays the same instead of increasing?
Yes, go on.
So I'm assuming in the one where both ends are pinned, the one is sort of like a universal, like one value, like the length.
Yes,
You
it
cannot
is.
go beyond one.
Because
In some
all
sense.
other values are in reference to this value.
Yeah, exactly. And in the two also, I'm assuming that since it's just because there's one free end, not because of.
Yes, in
Yeah.
figure number E as well, it's a cantilever condition. In
Exactly.
cantilever condition, one end is fixed and another end is pinned. So
The
in
fixed end
cantilever
is still
condition,
universal
the
one.
fixed has to be fixed if the cantilever has to stand. And
Yeah.
therefore it's reasonable to assume that the value remains unchanged. And you are right, and I'm happy that you're getting to the answer. But the only reason is I'm not getting at these explanations is because I don't want sort of you to confuse with a lot of information. I just want you to stick with what we are trying to understand. These numbers are all secondary. What we should understand is, what do these numbers mean? What when we say this is 0.5, this is 0.7. So what does this mean? Which one is going to have a greater strength, and why does this have a value of 0.5, and why does this have a value of 0.7? So the objective is not to remember these numbers. The objective is to understand what these numbers mean. Now, ultimately, we are going to have to remember some numbers. For example, we'll have to remember case number A, B, and D. We'll have to definitely remember these cases, and the values of 0.65, 0.8, and 1. We'll have to remember these. Okay?
Yes, thank you so much.
Any questions? Okay, if there are no questions, we'll quickly solve a numerical and try to understand this better. Please write down. Determine the design actual load. Determine the design actual load. Determine the design actual load on the column section ISMB 500. On the column section ISMB 500, given that the unsupported height of the column is 6 meters. Given that the unsupported height of the column is 6 meters. Assume the bottom is fixed and the top is pinned. Assume the bottom is fixed and the top is pinned. Assume Fy is equal to 250 megapascals. Fy is equal to 250 megapascals. Fu is equal to 410 megapascals. Fu is equal to 410 megapascals. And E, that is Young's modulus of elasticity, is 2 into 10 power 5 megapascals. Now it's been given that
So could you repeat the ISMB value?
ISMB 500.
Thank you.
ISMB 500, length 6 meters. So the bottom is fixed and the top is pinned. So if we go back to this chart, bottom is fixed and the top is pinned. The theoretical value is 0.7, but the code recommended value is 0.8. Therefore, we'll use the value of K as 0.8. So this is the given data, and we have to find out how much load can this particular column take. Now let us try to work backwards and then try to understand what are the steps to be followed. Ultimately, what we have to find out is what is load. Now, how do we calculate load? Load is equal to stress into area. Area is something that we know. We can refer to the steel table and we can compute the area for ISMB 500. Now, what is this stress? The question is this stress is equal to Fy? Is this stress equal to Fy?
Yes.
How do you know?
Because it's not it's only using the this thing, right? We're reaching a okay, I forgot the term.
this stress would be Fy only if the slenderness ratio is less than this value. So we'll get some slenderness ratio lambda p. You remember we looked at this. So all the columns that have lambda p of less than lambda p are short columns, and for these columns f would be equal to Fy, and all the columns which have a slenderness ratio of greater than lambda p are slender or long columns, and the stress would be less than Fy. Okay, so the question is what this F is. It's all about finding this F. And all the charts that we've looked at, all the concepts that we've looked at are about finding this F. The code calls this F as FCD. Now, let us just get familiar with the terms that the code uses. So for the force, the term or the notation that the code uses is PD. P is the action load and D is the design action load. Design compressive load is divided by PE. This is equal to AE, which is the effective area. It's the same as the cross-section area, into FCD. F is the design, stress, and compression. So these are the terms that the code use. PD is equal to AE into FCD. So we already know what AE is. It's only a matter of finding out what FCD is. So how do we get FCD? You just look at this curve, know the slenderness ratio, look at this curve, and we can get the value of FCD. But now the question is, which curve do we look at? Do we look at A, B, C, or D? Which curve do we look at? So for that, we have to refer to a particular table. Okay, so this table is number 10, which gives a buckling class of a cross section. So the buckling class can be A, B, C, D, depending upon what are the relative dimensions of various components. So here, we want to find out what is the buckling class. Is it A, B, or C, or D? So we are dealing with an I section. It's ISMB 500. We are dealing with an I section. So the buckling class depends upon what are the cross-section dimensions. So H is the total depth of the section. BF is the width of the flange. The first thing that we do is we calculate what is H upon BF, or what is the flange. If this is greater than 1.2, and at the same time, if TF, which is the thickness of the flange, is less than 40 mm, then the buckling class is A about the major axis, which is the Z axis, and it is B about Y axis. If the first condition met and the thickness of the flange is somewhere between 40 and 100 mm, then the buckling class is B about Z axis, and the buckling class is C about Y axis. Now, if this is too much information to take in, let me relieve you by saying that you will get this table in the examination. You can refer to this table while determining the buckling class. So you don't have to remember, what the conditions are and how to determine the buckling class. So if the height to the depth of the section to the width of the flange ratio is less than 1.2, then we look at these two conditions and then we determine what the buckling class is. Okay, so let us go back to our numerical and try to find out what is our FCD. So the first step is to determine the buckling class of the cross section. Before that, we need some data for ISMB 500 that we are going to use in this problem. Now let us go back to our steel code. So this is our I section. And we are looking for ISMB 500. So this is our ISMB 500. I'll just take the snapshot from here so that So this is our ISMB 500. So ISMB 500, the first thing that we need is a cross-section area. So ISMB 500 is a cross-section area of 111, but this is in centimeter square. Just remember this, 111 centimeter square. So the area of cross-section or the effective area is equal to 111 centimeter square, which is equal to 11100 mm square. Then next we need what is the total depth of the section. Now, one thing that I'd like to bring to your notice is that these notations might be different than the notation that the code is using. Okay, because these are different codes and they are revised at different times, so their notations might not match. For example, here the notation for the total depth is H. However, here the notation for the total depth is D. So don't get carried away by what this notation is. Understand what it means. So ISMB 500, since you are going to refer to this table, we'll use the notations that are given in this table. Okay, here the total depth is referred by H. So I'll say H is equal to 500 mm, which you can see here. Then what is the width of flange, which is denoted by BF. Here it is denoted by B. The width of the flange is 180 mm. So 180 mm. Then the next thing that we need is we need the ratio of KL upon R. But here there are two values of R. Okay, this is not the R that we are looking for. Okay, this is the radius of curvature of the section. This is not the R that we are interested in. We are interested in this R, which is radius of gyration. Now again, pay attention here. Perhaps I'll just open these codes side by side so that you understand what I'm trying to say. See here, the notations are a little different. Here, they say that the measure axis is X. IS 800 says that the measure axis is Z. Just a difference of notation. Principally, what it stands for remains the same. The minor axis is Y. Here also the minor axis is Y. Here, this depth is represented by capital D. Here it is small h. Here it is represented by small capital B. Here it is represented by BF. So, if you see something, if you see something else in the steel table, some other notation in the steel table, don't get confused. Understand what it means. So here, when we are referring to the moment of inertia or the radii of gyration or the moduli of elasticity, it's all Ix, Iy. Okay, so it is moment of inertia about x-axis, moment of inertia about y-axis. When you come here, it's z and y. So what we are going to denote them is we'll denote Ix as Iz and we'll denote Iy as Iy because y-axis is y-axis in both. And therefore, our Rz is equal to, it is Rx here, ISMB 500 is this, so Rz is 20.2. So this is 20.2. Again, this is centimeters. So 20.2 centimeters is equal to 202 mm. And the radius of gyration about minor axis, Ry, is equal to 3.52 centimeters. So 3.52 centimeters is equal to 35.2 mm. Please note that this is all subscript. Okay, so this is the data that we are going to require from the steel table. Now let us get to the actual design. The first step is determining the buckling class of the cross section. So to do so, we need the help of our code. So what do we need? First, we need to determine what is H upon BF. Here, H upon BF is equal to 500 divided by 180, which is equal to 2.78. Now we have to compare 2.78 with 1.2. So 2.78 is greater than 1.2. Therefore, we look at the first row. This row is not valid. We look at the first row. The second condition is the thickness of flange. So our thickness of flange is, oh, we did not look at it, sorry. So the thickness of flange here is denoted by capital T. So the thickness of flange of ISMB 500 is 10.2. Sorry. This is thickness of web. So this is our flange. This is the thickness of flange, and this is thickness of web, which is denoted by small t. So for ISMB 500, small t is the thickness of web, capital T is the thickness of flange, 17.2. Therefore, the thickness of flange is 17.2. Please note that the unit is mm, 7.2 mm. Now we go back to the steel code. Compare it with 40. This is less than 40 mm. Therefore, the condition that is valid for us is this one. Therefore, for buckling about ZZ axis, buckling class is A, as you can see here. So buckling class is A, and for buckling about YY axis, the buckling class is B. So the first step is over. We have determined what is a buckling class. So now we know which curve to look at. The second step is to find out what is the effective length. Now here the factor K is 0.8. Therefore, the effective length about Z-axis is equal to 0.8 times 6 meters or 6000 mm, which is equal to 4800 mm. Also, KL about y-axis is equal to 0.8 times 6000, which is equal to 4800 mm. This is our effective length. Step number 3, find out what is the slenderness ratio. Because the graph uses slenderness ratio and the buckling curve to find out what is FCD. Therefore, the third step is to find out the slenderness ratio. Again, we'll have two slenderness ratios. One is KL upon R about the Z axis, which is equal to, please note everything, everything is in subscript. I'm just relying on you paying attention and you knowing that it is in subscript, and therefore not really taking efforts to write down all this. So KL upon RZ is equal to 4800 divided by RZ. So what is RZ? It is 202. So 4800 divided by 202, which is equal to Can someone please give me a number quickly? I'm audible, right?
Yeah, 23.76.
23.76. What is the unit? Nothing, because it is a ratio. KL by Z, KL upon R for y-axis is equal to 4800 divided by RY, which is 35.2.
135.21.
135.21.
135.21.
I'm getting 136.36. Can someone confirm this?
Yeah, yours is.
Yeah, you're right.
Okay, so now we have slenderness ratio. Now we have everything we need. Now we just have to look at the curve. That's it. Okay, now we just have to look at, when we are finding out the buckling about z-axis, we have to look at curve A. And when we are looking at buckling about y-axis, we have to look at curve B. Okay, now the problem here is that it's just using the information that is given in this curve. How do I accurately determine, what FCD is? It's difficult because it's a graph, and it's something that I'll have to use, a very accurate scale to interpolate between this, and then again go to this curve and then interpolate again to this value. The purpose of the code is to really simplify things that can be easily used. So what the code does is it goes one step ahead and gives these curves in terms of a graph, in terms of a table. So if I go to the next pages, okay, so here the code gives the values of these design compressive stress for column buckling class A. Okay, so it gives all these values for different values of slenderness ratio. And then these various columns are for different values of Fy. Right? Now let us sort of look at the trend in these values. For a particular value of KL upon R, the value of FCD increases as the yield stress increases. It's obvious, right? Do you understand what I'm trying to say? No? Okay, let's do it one more time. So for a particular value of slenderness ratio, the value of FCD increases. So this is 182, this is 191, 200. As the value of Fy increases, which is obvious, a material of higher yield strength can surely take larger amount of stress. So for a particular, if the K value of R, K by R remains the same, the material with a higher yield stress will have a higher value of FCD. Now, if
does it increase proportionally along with the Fy, or is it kind of a curve along the straight line of Fy?
So now that's hard to say, because it will depend upon what is the slenderness ratio. For example, here, see the value increases from 227 to 236, but here the value remains the same. Here the value is, so it depends on in which portion of this curve are these values.
Yeah, that's actually what kind of confused me.
It depends on which portion of this curve are these values. Okay. But principally, we are just trying to understand what does this table mean, and what do these various numbers that are given in the table mean. So for a given value of scalar, for every value, you'll see that when you go along the x direction, these numbers will always increase. That is what is expected. the material that has higher value of yield stress will surely take more load. That's what it says. For example, you look here, 220. These values are always going to increase towards the right. Okay. Then when we go in the vertical direction, for example, if we say Fi 250, as scale upon R increases, all these values decrease because yield stress, or this is because the critical stress is inversely proportional to KL upon R. So as KL upon R increases, FCD and hence PD decreases. Okay, so what do? We just look at what our yield stress is. If we go back to the question, our yield stress is 250 megapascals. You go to this table. So we are going to deal with buckling class A. So this is the table for buckling class A. Now we have 4 such tables for buckling class B, C, and D. So we are going to look at buckling class A. In buckling class A, we look at our yield stress, which is 250 megapascals. So you just look into this column. In this column, there are various values for various values of KL upon R. Now, if we go back to whatever we have computed as of now, the KL upon R about Z-axis is 23.76. Okay, so we go to the steel code. For 250, we look at a number between 20 and 30 because we have to find out the value of FCD for 23.76. Now this table does not give a value for 23.76. That is something that we'll have to do, but we look at the values between 20 and 30. So we look at for 20, the corresponding value is 226. For 30, the corresponding value is 220. So our values lie somewhere in between. And let us try to find out what this value is. Okay, so for ZZ axis, the buckling class is A, and AL upon R, the slenderness ratio is 23.76. So I'm just pasting it here so that we can refer to it easily. Okay, so for so this is KL upon R, and this is SCD. So what we have is for a KL of KL upon R of value of 20, we have this value is 26. For 30, we have value 220. So for 20, this value is 226. For 30, this value is 220. We have to find out the value for 23.76. So 23.76. Let us say this value is X. Now, does someone know how we can find this value of X? By linear interpolation. Heard of this term before, interpolation?
Is it similar to graphing it out?
Yes. So see, we can do it this way. 23.76 minus 20 upon x minus 226 is equal to 30 minus 20 upon 220 minus 226. Look at it and tell me if you understand this.
So this proves that depending on where they are on the graph, there is still some relation between the values. Like we discussed earlier, right?
Yes. So what we are doing is we are linearly interpolating our value between 226 and 220 to find out what is the value of FCD corresponding to KL upon R of 23.76. So what I did is, so this minus this, which is 23.76 minus 20 upon x minus 226 is equal to 30 minus 20 upon 220 minus 226. It's called linear interpolation. Or if I have to graphically tell you what we are doing is, let us say this is our graph and so this is our graph between KL upon R and FCD. Okay, so this value is KL upon R, FCD. So if let's say this is 20, this is 30, the scale upon R is on the x-axis. Corresponding to this, this is 226 and this is 220. Now we want to find out what is the value for 23.76, whatever. So we just have to find out this value. So we do a linear interpolation. So this is how we do a linear interpolation. Is it clear? See, there are no questions coming from your end, therefore I highly doubt if you're understanding what is happening here. Okay, again. Are you understanding what we are doing?
When you explained it on the graph, it's kind of simpler. So we got
Okay.
it now.
Okay, perfect.
So Bhargav, if I have more values below and above the number that I'm finding, will it give me more accurate results since this is still slightly inaccurate, right? It's an approximation of the answer.
What is an approximation?
X will still be an approximation of the actual value of FCD, right? It won't be a direct value since we're using a straight line on what's supposed to be a curve.
Yes, but we can just, you are right. But it's a fair approximation because already the values are at a very close interval.
Right.
So you're not going to get a value that is very different from linear interpolation.
And there's no way to make it more accurate by like taking multiple by taking multiple ranges and getting an average, right?
Yes, but then how will you do it?
I
So
take
for that,
20, 30, I can take 20, 40, 10, 30, and I'll get multiple answers close to X, and then I take an average of them or a median of them. Well, average fraction of myself.
yes, you can do that. But just trust me on this, and if you do it
It's
this
not-
way, you will get an answer that is close to an actual value.
Yeah, we don't need that direct exact answer anyway.
Yes.
So,
Oh, this is stuck. Give me a moment. So can someone please give me a value of x?
Is it 217.97?
X is equal to 217.97. Can someone confirm this answer?
I got 223.744.
223.74. Any more answers?
Yeah, I got it as 28.256.
220.
8.25.
I got 223.84.
223, so close to this.
Yeah.
Yeah, same 227.
Okay.
228.256.
228.256. Okay. Now, how do you look at these three numbers and eliminate the wrong answers?
So it can be less than 220 and greater than 226, as the 23 comes between 20 and 23. So the right answer will be 223.74.
Exactly. So since this number is between 20 and 30, our range of answer should be in between 226 and 220. Anything that is less than 220 or greater than 226 automatically incorrect.
Yes, I messed up my signs at 228. It's 223.74. I messed up my signs.
So I hope you have enough confirmations to say that this is the right answer, 223.74. What is the unit? Unit batao.
MPa, megapack.
MPa, because this is stress. So our value of FCD is equal to 223.74 MPa. Now, one thing to remember here is that this is for buckling about Z axis. Okay. So now we have to repeat the same thing for buckling about Y axis. So for buckling about Y-axis, the buckling class is B, and the value of KL upon R is 136.4. The buckling class is B. Therefore, For buckling class A, we refer to table 9A. For buckling class B, we refer to table 9B. Now here our Fy is 250 and our KL upon R is 136. So which value should we look at?
$130 and $140.
So this is KL upon R. This is FCD. We have to look at, as he rightly said, we have to look at values between 130 and 140. So 130 and this is 136.4. This is 140. So for Fy 250, 130 corresponds to 81 and 140 is 71.8. So this is 81. This is 71.8. Okay, now again calculate the value of x. So 136.4 minus 130 upon x minus 81 is equal to 140 minus 130 upon 71.8 minus 81. I am getting 75.11. Can someone confirm this answer?
Yeah, the same.
Okay. Therefore, FCD about y-axis is equal to 75.11 MPa. Okay. So now we have two values. This is our second value, 75.11, and this is our first value, 223.74. Now, if you compare this, first value is much greater than second value. What does that mean?
It means that it would probably bend on the buckle on the y-axis because it's like much smaller.
Exactly. It means that buckling about the minor axis acts as a lesser value of actual load. And that is why when you hold, the steel ruler in your hand and you try to press it, it buckles about the minor axis easily. So this value of buckling stress is much lesser than the value for major axis. So now the question is, which FCD should we consider? Should we consider the first FCD or should we consider the second FCD?
You consider y, right? It is a smaller value.
We have to consider the one that gives a smaller value. FCD of Z, FCD for bending about y-axis. So this is equal to 75.11 MPa. This is our design stress. Now the last step, which is I think step number 4. Yes, step number 4 is to determine what is the value of PD. PD is equal to AE into FCD. So our effective area, 111, something that we already found out. This is equal to 11100 times 75.11. Give me an answer.
833721.
Unit. यूनिट बताओ.
Newton.
833721. Newton, because force, it is force, which is equal to 833.7 kilonewton. This is the number that we need. So you can safely apply a force of 833.7 kilonewton on this column. Okay. So now, if we know that the value of FCD about Y is always going to be less than FCD about Z, then why did we find out these two values? Did you understand my question? If we know that this value is going to be lesser than FCD for Y, FCD for Z, then why did we find both these values? We did just to get a feel of how these values are different or how much is the difference between these two values. So what will you do in the exam? In the exam, there is no need for finding out these two values. So what you will do is you will you will follow this step number 1, step number 2, step number 3. Once you have reached here, you will say that KL upon R of Y is greater than KL upon R of Z. Therefore, this governs the design. And therefore, you will not follow this step. You will not follow this step. You will resume from here. Do you understand? Is there any confusion? We found out both these values just because we wanted to sort of understand how different really are these values. Or how easier is it to buckle about the minor axis as compared to that about major axis. Do you want me to repeat this? Am I audible?
I think we understood.
Okay. I think everybody else shares the same feeling. At least I have to assume that because there's no response.
Yes.
Okay. So this was just for your understanding that we found out both these values. In actual examination, you will not find the FCD corresponding to Z. You just go to the third step and say that KL upon R of Y is greater than that of this, therefore it governs. And you just find out the value of FCD for KLR about Y-axis.
So you just skip the extra step of calculating for everyone.
Yes. And this is the easiest, and this is in terms of its length, it is the smallest problem or smallest numerical that you'll encounter in the examination. Okay, so I'll share the presentation today. You already have the numerical. Take your time to understand everything. And if there are any questions, we'll discuss it in the next lecture. And in the next lecture, so we are not done with compression members yet. There are just some topics that are left, but very minor topics. But they're important from your project point of view. There's just a list of sections that you can use for different type of structures. So this is something that I want to cover. And then finally, there's another type of problem that we want to cover, in which now in this problem we knew the section and we wanted to find out how much load can this particular section take. These types of problems are called as analysis problems. We looked at the difference between analysis and design problems. But in actual practice, what we get is the load, and we have to find out which section can we use. That problem is called as a design problem. So we have looked at the analysis problem. In the next lecture, we'll wrap up the remaining theory part and we'll look at the design problem, in which we, the actual load value would be given to us. And from this actual load value, we will find out a section that can take this load.
So we can apply the formula in a different way.
Yes. So the fundamentals remain the same. Only the approach changes slightly. That's it. Just one. This is one additional step.
I had a doubt from last time, but it's more general and like related to any specific topic.
Yeah.
So when we look at the failure of a member in terms of a tension member, we still look at it as like part of it undergoes compression and part of it undergoes tension, right? Like the lower part undergoes tension and the upper part undergoes compression when it's sagging. So why don't we analyze a compression member in that same way that, the compression member also starts swelling, or you have buckles at one end, which kind of have, when in buckles, there is a certain compression on one side and tension on one side, right?
Okay. So when you say that there's tension on one side and compression on other side, that is that's a local phenomenon. If it is capable of developing a yield stress, then it has the same yield stress capacity in tension and compression as well. But the problem is the geometry does not let it reach yield stress. Before that itself it buckles. So now it's not a matter of tension or compression. The matter is at what value of stress, at what value of compressive stress will it buckle. So there, even though because of bending, okay, let me again put it in a way that I think will be clearer. Okay, so if I have understood your question correctly, so let us say that this is our column in elevation, and say under the axial of an eccentric axial load, it buckles like this, right? So there is compression here and there is tension here. So why is it that we are looking only it as a compression member and not as a tension member?
Yeah, when it's buckling, it's still undergoing tension in some parts, right?
Yes. So now let us try to look beyond its deflected shape to understand what is happening. So when a column is under pure axial compression, let us say the actual load value is P. What is the stress at any cross section? The stress at any cross section is P upon A. Simple.
Yeah. Yeah.
Now what happens is that if this load acts on an eccentricity, so if it does, then you will have an additional moment which is equal to P times that eccentricity. And because of this, just a moment. So if you're talking about an additional moment, so let us say that this is the additional moment, which is equal to P times E. I hope I don't have to go back and explain how this, why do we have an actual load and additional moment.
No, that's clear.
So because of this moment, now you will have, let us say, okay, this is, it all depends upon the magnitude of moment, but let us say that you have tension in some part and compression in some part, and then your stress diagram is something like this. So there is tension in some part and there is compression in some part. This is tension, this is compression, this is compression. So what is actually happening is it is the sum of these two because both of them are acting at the same time. So finally you might get something that is this. So let us say this is stress C1, this is C2 and this is T. So here it would be C1 plus C2. Here it would be C2, oh sorry. Here it would be C1 minus T. But still overall it is under compression.
So the tension is not an important part in its failure, essentially.
It will be, see, we are talking about only compression members. We're not talking about beam columns as of now. A member is beam column when there is a significant moment. And when there's a significant moment, there would be a significant tensile stress and a significant, corresponding compressive stress. And then, the resultant might look something different. Then the resultant might look something like this. We are not looking at those kind of members right now. Their treatment is different.
Okay, understood.
We are looking at members that have only axial load. Okay, and under the axial load, there is some buckling occurring, and we're just trying to find out the stress at which it buckles. We are not treating it as some portion being, a tension member and some portion being a compression member. We're not treating it that way.
Thank you.
Okay. Any more questions?
I had a question. The next class is on the 18th, right?
Next class is, why not on 11th? Is it a holiday?
I thought it was part of the Ganpati day.
Okay. It's on 10th, right? So there must be an official holiday on 10th and not 11th.
But we've been given a vacation from college from 11th to, I think, 4 days.
Okay.
Even my electives are not being held this next week, I think. That's what Manu told us.
Okay. So do we have any vacant slot during the weekdays? In the morning? So let us figure it. I and the CRs would figure it out. But we will have to have a class because I understand that initially, it was a 16-week semester. Now, because of some reason, it has been converted to a 15, week semester, out of which we have lost one lecture, the first lecture, because of some reason we could not conduct it. So even in this 15 week, we are short of one lecture already. And if we skip one more lecture, and I think again, unfortunately, there's a holiday on 2nd October. So, we're going to have to adjust a little bit. So there's one lecture that is already pending. So we'll have to have this lecture. in some other time slot. So we'll figure it out. Any questions related to what we just learned?